right, we'll get started here. We're live. Let's do it. All right. Okay, so number 2. So you've got the nickel block, and it's 10 kilograms. Nickel block on a Teflon surface. So notice the coefficients of friction are pretty low because Teflon's pretty slidey. So do the force diagram. How much downforce is there? 98 newtons, which means there must be normal force of 98 newtons. The first one says, let's say we push this block to the right with 10 newtons of force. Well, you probably don't need, well, I guess we should look at the calculation because it's not obvious off the bat. But you might go, well, how much static friction can this surface provide? What is his maximum amount that he's able to do? So you're going to go, the force due to, let's say, static friction. I know writing a subscript that's 2 whole words is annoying, so maybe this makes more sense to write like this. Sure, add abbreviation and maybe say something like static. So for the static scenario, you have the force of friction is anything up to mu sub s times the normal force. So that's what you missed yesterday. Emily, it's just like basically these are dimensionless quantities. They don't have units because when you multiply the coefficient times the normal force, it's like newtons times no units makes newtons. So anyway, you got, so for the static scenario, it's going to be 0.15 times 98 newtons. And so what is that going to be? 14.7. Okay, so what we see here is that, is that the floor, the surface, is able to produce up to 14.7 newtons of friction force if the block's not moving. So does everyone understand that? Sure. Okay. So then come back to the picture and say, well, if he's able to produce this much force, when he feels the 10 newtons, he's just going to push back with 10 newtons. And then the net force would be 0. And the acceleration would be 0. Cool beans? We understand? Okay. Now, the next problem, we right off the bat know, if we push it with 20 newtons now, make a new force diagram. Now we're going to push with 20 newtons, still 98. 98. Markers. They don't make them like they used to. Back in my day, it's no marker. Oh, that's much better.
When's your birthday, Mr. Paul?
When's my birthday? September.
Dang.
Why?
I would have got you a pack of markers.
There's like a billion markers in the room, but thank you.
Wait, really?
The room. There's like a little storage closet over there. Luckily, Miss Workus is very responsible and like orders all the markers on time. When she retires, we're probably going to have like a huge marker shortage. We're all going to go in there and be like, "Where's the markers? Miss Workus isn't here to order them." Seriously, go in there, everything you could ever need, all like the materials you might need, and then
it's also pretty organized too.
It's very organized.
Yeah,
That's awesome.
If it was me, it'd be literally a big, one of those like big 10-gallon buckets with just various like pencils and markers and notepads and graph paper, just all thrown into the big bucket. That's what it would be.
Just a sign above it says get ready.
Yeah, just get your supplies. Okay, so anyway, we know that if you overcome this force, so this is the max friction force that we can get out of the surface interaction. So if you exceed that, then what's the friction force formula now? This is going to start sliding, right? Makes sense? So once you exceed this number, you start sliding. And then once you start sliding, you need to look at the kinetic coefficient instead. It's still the same formula pretty much, but the big difference is it's an equal sign instead of an inequality, and it's the kinetic coefficient instead of the static coefficient. So my friction force I get now is 0.12 times 98 newtons. What do you get there? 11.76 newtons. Or call it 11.8 if you want, it's fine. So now, if I write F net equals MA, what's the net force? Yes. Everyone understand that? Because it's just this minus the friction. So 20 minus 11.76. The mass was 10. If I solve for acceleration, I get a pretty small number, 0.824 meters squared. There we go. Cool beans? All right, to answer part C, we go down here. So the first one was part A. This is part B. Part C is pretty short. It's just what's the minimum amount of force required to get the block moving? Well, to get it moving implies it was at rest, so 14.71. Just make it slightly larger. That's not a technical answer. I'm just kind of joking. As long any force that's larger than 14.7 will get it moving. That's what we talked about yesterday. Yeah, 14.7000001, just the tiniest bit more. Now, realistically, if you exert 14.71 newtons, it's not going to accelerate very quickly. It's going to be a very tiny acceleration until once it actually gets moving, the friction force will drop down to this. So you actually will have a decent net force of about 3. Okay, D says if the block is being pushed to the right and experiencing a rightward acceleration of 2 meters per second squared, find the force of the push. So what should we do here, guys? How do we figure this out?
Well,
We know the acceleration.
and we have the mass.
Give you a quick little force diagram.
Sure.
What are we solving for? Yep, the force of the push. Do we know this number? It's this number. It's 11.76. Now, why is it 11.76 instead of 14.7?
Because, yes.
It's moving. That's a very concise
Yeah.
and good answer. Why is it this number and not this number? Because it is moving. If it's moving, you're in the kinetic scenario. Okay, so if I write F net equals MA, so I'm getting kind of crammed here, but F net is just this minus this. So the force I'm solving for minus the 11.76. The mass we said was 10, and the acceleration is 2. So the answer to this question is going to be 31.76 newtons. Did I say that wrong? 31.76. Right? Because I just multiply those, get 20,
Yeah.
and then add this over to the other side. Yes, no, maybe?
Oh, so.
Yes.
By the way, let's simplify this real quick. For question D, without doing anything fancy, do you guys see how if you know the acceleration and you know the mass, then you know the net force is 20?
Yes.
That's another way we could have looked at it is started off with, I know the net force is 20. So what kind of rightward force would be necessary to get a net force of 20, given that the leftward force is 11.76? That would have also given us the answer 31.76.
That makes sense.
Cool beans? Okay, how much force, so part E, how much force do you have to apply to the block to accelerate it from an initial velocity of 2 meters per second up to a final velocity of 20 meters per second over a period of 6 seconds? Do you guys see how this question is identical to D with one extra step? Yeah, what's the extra step?
You gotta solve for acceleration.
Right. So what is the acceleration if you're going from 2 up to 20? Over 6 seconds, 3 meters per second squared. So the same exact setup, but now the A value is 3, and so your answer is going to be 41.76. Do we all get that? All right, so let's move on. 3, 4, and 5 can be kind of try to solve them on your own. They may challenge you. It's kind of the point, but it's this, the principle is exactly the same. Let's do this weird thing with this pulley, number 6. Pulley.
Mr. Hall, what is daylight savings time? November 1st. November 1st?
Yep. Oh, sweet. Then we get an extra day.
What?
Or no, we get an extra hour.
Make it a national holiday.
Yeah.
Savings, not day savings.
We get an extra hour. That's what I meant to say. Yes, that means we get a 25-hour week. Sweet.
25-hour weekend.
No, it's 25 days. It's 25 plus.
I don't know how the
Let's
light
get a
saving time
49-hour weekend.
works. I have no idea how that works.
They're gonna make the clocks go back an hour. So like right now,
You get 2 o'clock.
say the sun rises at 8 a.m., right? After daylight savings, it'll be rising at 7 a.m. You set the clocks back.
How that works. Like, why does the sun rise an hour earlier? Like,
Well, the sun's rising at the same. Nothing's changing with, like, say, the sun and the earth. It's just obviously, it's just that we are taking our clocks and setting them back. Like, I mean, imagine if everyone agreed to like set the clocks forward 7 hours. It'd be so weird.
Yeah.
Right? Like the sun would rise and you'd be like, oh, it's like 4 in the afternoon or something, whatever it would be. You'd be like, what the heck's going on?
Yeah.
So yeah, the clocks. I always feel like since we live at a high latitude, that we should set our clock. We should have like our own thing where we set our clock so that, like, say school starts at an hour after sunrise. You can do that by adjusting the clocks, or it's by adjusting the schedule, saying, oh, okay, well, in the winter school starts at 10 a.m. or something. But-
School start a lot. Like, we go to school. So.
Well, like in okay, you get what I mean. Though, like in spring, like the sun.
Yeah, when the sun's coming out at 7 a.m., I would start school at 8. If the sun comes out at 8:30 a.m. or whatever. That's why I kind of like daylight savings, because yeah, right now it's like I wake up and it is pitch black outside.
Yeah.
During the school, in the darkness.
Yeah, it's pitch black. So I'd have them set the clocks back 2 hours. That's what I would like to see. So then by the time the sun's coming up, you're like, oh, it's only 7 a.m. or something. So that'd be nice.
Arizona, why not do it?
Yeah. Arizona, federal.
There was a time when I know this might be obscure, but so there's a famous soccer tournament called the Champions League. It's like bigly famous. But anyway, it was in a city in, I think, Ukraine, where half the city observed daylight savings time and half didn't. And the stadiums were in different sides of the city. So when you look up, like, what time is the game starting, it was extremely confusing. They'd all be at different times. Be like, well, is that this half of the city that doesn't have daylight savings, and anyway, it's weird. So
Yay.
Very confusing.
yeah. So luckily here we're all on the same page. But that makes sense. So yeah, so we're just moving the clocks so that they kind of more agree with what we think.
Oh.
Yeah.
They work rough.
It's intended to make it more like so that you're not going to work in pitch black darkness. But at our latitude, it's kind of unavoidable. You're either going to work in the dark or you're coming home in the dark. Unless we switch to like a 24-hour work week, then we might be okay. Just saying. Yeah, Winslow's gonna do one 24-hour shift and then be done for the week.
I think it's perfect. Doesn't sound too bad.
It's like, so you focus for like an hour and a half, there's no way.
If you're that man caffeine, you will see that man focus.
Perfect.
It's all done. And they're all pleased, though.
6 days to do whatever you want. Nothing amazing.
So,
You could actually get 13 days, because if you worked like on a Sunday, and then you didn't work that whole week, and then the next week rolls around, you don't have to work till that Saturday.
okay, number 6. This the block on the table is 50 kilograms, and there's like a pulley that attaches the 2 blocks by a string or a cable. Okay, and then there's a 40 kilogram block hanging off the cable. So does the setup make sense? Hello, Jesse.
Hello. How are you?
Good, how are you doing? Thanks for visiting us. Okay, so the question is, if this is in static equilibrium, that's a fancy word. Static. Can we all figure out what that means? Not moving, and it's not about to move. It's stable. It's stable. It's an equilibrium. There are such things as, you could have an unstable equilibrium. I'll give you an example. Like if you had like a little hill, and then you put a marble at the top of the hill, tiny little like bump could send the marble in either direction and would leave. Versus a stable equilibrium would be like a little valley. Put a marble at the bottom. If you bump the marble, it's just going to come back to where it started. So anyway, fun word of the day. That would be unstable versus stable equilibriums. Equilibria. Anyway, static equilibrium is a word you'll see a lot. It just means that the system is static. It's not going anywhere.
So like when my mom tries to get me every morning, just
And
say,
you're-
Mom, I'm
I'm
at static
in
equilibrium."
static equilibrium. Okay, so let's analyze each block's force diagrams. This guy, well, he's got, how much downforce is there? Pushing him against the table.
Gravity.
Gravity, so that would be 490 newtons. So the normal force has to be 490 newtons because he's not going up or down. What is the name for this vector that's trying to pull him off the table? Tension. So the force due to tension is, I'm not really sure yet. And then what must be happening over here? If it's in static equilibrium, there must be a friction force that is equal to that force. That makes sense? If this was smaller, what would he be doing? He'd be sliding. No?
Okay,
If he's-
No, I was just picturing it as a conveyor belt instead of a pulley for a second, so I was good.
Conveyor belt relies on friction, though. If there was no friction, the belt would move and the object would just stay put on top.
Have you seen that one video where the conveyor belt is bringing a box up, and the box like falls and it just keeps doing this number?
Yeah, I've seen that. It's a good one.
To Mr. Hollis, taking a shot like I saw that, would you just take then the 40 times gravity, or is that correct?
Yeah, so now you have to say, well, I got to figure out this number. So you come over to this part and you say, well, from his perspective, ignore everything else. Pretend like, you take a big piece of paper, for example, and cover this all up and say, actually, his force diagram is very simple. He, again, is in static equilibrium. So there must be 392 newtons pulling him down, gravity, right? 40 times 9.8. And there must be tension in the rope. Now here's the big, physicsy thing here, which is that these two tensions are one and the same. Now that may or may not be intuitive to you, but that's the way tension works. So if you have a string and the string is pulled taut over, say, a pulley, the tension is going to be the same throughout the entire string. But what's kind of weird is, if you ask this guy, what direction does the tension pull you? He says this way. But if you ask this guy, he'd say the tension pulls me this way. And the same thing when you here's you trying to catch a big fish. Fishing pole. Big fish. If you fish, you've experienced this, right? You're pulling, right? You're like, wow, I'm really getting pulled towards the water. And the fish is like, I'm getting pulled up towards the surface of the water, because that's the tension of the string is existing in both directions throughout the string, right? Or say tug of war might be a better analogy if you've never fished. But so that tension is doing two things. It's pulling this block that way. It's also pulling this block this way. So anyway, now I can come back to this diagram and I can go, okay, the friction force must be 392, right? So if I go, so friction force is mu static times normal force. And we know, what's that number? How big is that number? It's got to be 392. Mu static's what we're trying to find. And the normal force exerted on this block is 490. And so we get, now here's where the inequality is a little funny. If you read the question, it says, the bucket can hold a max of 40 kilograms. So this means we are actually maxing out our friction. So I can say that when I solve this, I can actually make it an equality. Does that make sense why that maximum is important? Really, I mean, in hindsight, I probably should have done this. Because do you guys see how, look at the number we get. We end up getting 0.8, right?
Yeah, you use equal because it's at the perfect point, right?
Well, so do you guys see how this could still be in static equilibrium if mu was 1.7? Like if mu was big, say it was two really grippy surfaces, right? It was like a gecko. I guess geckos, is that actually friction? It's more like adhesion, but I guess friction involves some adhesion. Anyway, sorry. Say it was two really grippy surfaces, rubber and rubber, right? It would still hold in static equilibrium, right? It doesn't necessarily have to be this number, but this is actually the minimum value of mu that makes it work. So the way this is phrased is, if you say pour sand into this bucket and 40 kilograms is the absolute most you can put in, then that tells us kind of the breaking point of the friction. Is that confusing or does that make sense? So maybe you got me. So I guess to understand that, what I would say is, imagine that it didn't say maximum. Imagine it just said 50 and 40 and it's in static equilibrium. Then what I would say is, then the answer would be mu could be anything greater than 0.8. That would be the answer. So think about that. But if we know that's actually the maximum, then that is truly the static coefficient. So you'll figure out 7. I know you will. I believe you'll do it. How are we doing? Okay. Okay, I'm going to give you one more example, and then we're going to be set to just kind of be done with friction for a little while until we come back to it. Let's do 8 together. Actually, no, I think you guys will have no problem doing 8 and 9. Let's do a trickier one. 10 sneaky. All right, so read 10. The coefficient of kinetic friction between a car's tires and the road is 2.6. If the car is traveling 40 meters per second and then slams on its brakes, so that it slides across the road, how far will it travel before coming to rest? Does anyone know why I included the wheels locking up and sliding a bit? True. Yeah, exactly. Well, I was thinking of anti-lock brakes. That would greatly complicate things. Yeah. You guys know how those work? Yeah, they go. There's a computer in there that kind of like figures out like because it's way better. In the old days, they would try to like hit the brakes like this, because if you just slam on them, they lock up and the wheels just slide and they'll slide farther. So they used to try to kind of like pump the brakes a bit, but a computer can do that way faster, and it like pumps the brakes extremely fast. If you ever have your ABS turn on, you'll hear this like.
That's interesting. It's like whenever my dad, you want me to drive that way, to like pump the brakes.
They
So I don't know
yeah.
what my car.
Yeah, they say it's a point of confusion, because they say, well, yeah, people in the old days used to learn, don't just hit the brakes. That's bad. You're going to lock up the wheels and slide. But ever since anti-lock brakes have existed, they say, well, the anti-lock brake system is designed for you to just slam on the brakes as hard as you can. So it just depends. Do you have that system or not in your car?
Yeah.
So anyway, I think still generally, if you can avoid engaging the system, it's probably better. Like if you're on an icy road and you have plenty of room to come to a stop, it's better just to very gradually slow down. But
Right.
if you already know if you're going to hit someone, you want to just try to let the anti-lock brakes do their job.
Is air resistance technically a type of friction?
I mean, kinda. The difference is, air resistance, there's a whole lot of weird stuff going on. Well, same thing in friction. Friction is like a very complex phenomenon. There's a whole bunch of different, there's like intermolecular forces going on, and that all kind of contribute to this macroscopic phenomenon of friction. Same thing with air resistance. Like, for example, when you're traveling through air, first, in the simplest terms, is there's always like little pieces of mass. So later on in this class, we'll talk about momentum. And so every time you bump into one of these little particles, you're kicking it off in this direction, and you're imparting momentum to it. So every time you hit something and give it momentum, you lose some of your momentum. Like in sports, you run into some guy, even if you run over a little guy, you still lose some of your speed, right? Even if you're playing football with a bunch of 10-year-olds, you still you run that guy over, and it's still, even though he was only 80 pounds, still slows you down anyway. So like that's going on, but then also like as you move through the fluid, you get these little vortices, and like the fluid tries to like kind of stick to the surface as it goes past it. So there's all these things going on. There's still open problems in physics about like if you can solve certain equations involving fluid motion, you can like get $1 million and become famous. So it's pretty neat. Huh? Which one?
I don't know, the guy that was like, broke the equation and I figured it out and didn't like take the credit for it.
Oh, yeah, that guy, Grigor Perelman. That's the Russian guy, yeah. That was a pure math question. I'm trying to remember what the flow one is called. I'll look it up real quick. It's a millennium problem. It's the Bernoulli equations, I'm pretty sure. Or Navier-Stokes, actually. Navier-Stokes is what it is. So yeah, there's a problem out there called the Navier-Stokes equations. And if you can like solve that problem, $1 million. So get on it, guys. Have I told you guys about George Danzig? Oh man, that guy was so lit. This guy goes into his graduate statistics class, and the professor had written 2 problems on the board. This guy came to class late, and he goes, "Oh, that's my homework." So he writes down the homework problems. He goes home. They're really hard problems, but eventually he solves them. And he comes in like the next class and he's like, man, this problem's really kicked my butt, but I figured them out. And the professor was like, bruh, those are just two examples of unsolved problems in the field of statistics, and his solutions were apparently valid. And so they're like, well, I guess you got your PhD. It's right there. Like, there's your thesis. Like, you're done. And so that's the story.
That's awesome.
So, and I guess, the moral being, he didn't, if someone had, he even said, like, if someone had told me these are unsolved problems, lots of super smart statisticians have tried to solve these unsuccessfully, he probably would have been like, oh, okay. But since he thought they were solvable, he like tried really hard and eventually solved them. Anyway, like if you cry every time. Okay, Mr. Carr. I don't know I think 2.6 might be an unrealistically large friction coefficient, but oh well. Think about what that means. That means if I weigh 1,000 newtons, then that means the floor can generate 2,600 newtons of friction to prevent me from moving. So that's a lot of grip, but maybe it exists. I don't know. Those football gloves where you can like one hand catch it.
Yes.
Maybe. But again, there's stickiness. I think there's a difference between stickiness and friction. But anyway. So what makes glue work is not really, I wouldn't really call that friction. Okay, so he's going 40 meters per second. He hits the brakes. He slides. Now the question that we don't know is this: how far does he travel? What's his displacement over this event? What's his final speed though? 0. Okay. And we know that mu is 2.6. It doesn't say mu sub k, but it says coefficient of kinetic friction. And the thing's obviously sliding across the ground, so we're dealing with kinetic friction. So sometimes it'll just be, you just got to know from the context of the question. Are we talking about kinetic or static? This one clearly is kinetic. So
Are we doing?
yeah, so this probably suggests that maybe the time-independent equation is the best way to go, to use this. V final squared minus V naught squared equals 2 times acceleration times delta x.
So you get the acceleration through Neil.
So yeah, we can see that we know these two numbers. Can we maybe figure out this number, and then we'll be done. So let's do that. Let's look at the force diagram for the car. Here's the car. How much gravity is pulling him down?
MG.
mg. So what's the normal force? Okay. Now, is there any force required to have him moving forward? Nope. Remember, we're not ancient Greeks that thinks impetus exists. We are modern day Newtonians. But what has to be there to slow him down? The friction force. Now, the friction force is just going to be mu times mg, right?
Yeah.
That makes sense? So if I go F net equals ma, right? What's my net force in this problem? 2.6 times mg, right? 2.6 being the mu value, right?
Oh.
Now, here's the amazing thing. Someone must have been thinking, wait a second, you messed up. You didn't give us the mass of the car, right? Reasonable objection. But it turns out, look what happens. It canceled out. So the acceleration of the car, it turns out, is really just 2.6 times g, which is, what does Mr. Quackulator say? 25.48. So then all you got to do is plug that into your A in this equation, and you'll get, yeah, so it'll end up being 40 squared divided by 2 divided by 25.48. Cool beans? Okay. All right, see you tomorrow.
See you later.
Oh, see you later.